Electron affinity is the opposite of ionization. Ionization always deals with the creation of positive ions, while electron affinity is a negative ion equivalent. Electron affinity is especially important when dealing with exothermic chemical reactions, which release energy. Examples are a candle flame and condensation of rainwater from water vapor. All in all, electron affinity is essentially the likelihood that a given neutral atom will gain an electron.
So essentially what we have here is a Bohr model of a single atom of lithium, which can be represented with the electron configuration of 1s2, 2s1, with 2 electrons on the inner orbital and 1 on the outside. This is a neutral atom because there's the same number of protons in the nucleus as there are electrons. Now, we've already established that electron affinity is essentially the likelihood of a neutral atom such as this of gaining an electron. So if we were to make this into a negative ion, or an anion, we would add an electron, changing this electron configuration to 1s2, 2s2. So there's 3 major factors that play into electron affinity. And the first one is nuclear charge, which is essentially the attraction between the positively charged nucleus and the negatively charged electron, which makes sense because opposite charges attract. The second piece is known as electron shielding, which is that these inner orbitals will repel the outer orbital and shield it from the full effect of the nuclear charge. The third piece is distance. So the closer the distance between the electron and the nucleus, the more attractive force will be present. So overall, there's an attractive force that this atom has for this electron, which is known as electron affinity. So this atom has an electron affinity for this electron. This means that it gives off energy when you add an electron to form this negative ion.
When speaking in terms of nonmetals and metals, nonmetals like to gain electrons to reach a fully stable octet, while metals like to lose them. Thus, nonmetals have a higher electron affinity than metals. In addition, electron affinity increases as you move along the period and decreases as you move down a group. The factors which affect this attraction are exactly the same as those relating to ionization energies. The nuclear charge of the protons of the element pull electrons in. This is why the electron affinity increases along the period, but it decreases as you go down a group because the valence electrons move further away.
Alright, typically when talking about electron affinity, as you go across the board, elements tend to give off more energy as electrons are added. However, there are 3 exceptions to this: beryllium, nitrogen, and neon. Beryllium is actually quite stable because its 1s orbital and 2s orbitals are both filled. So adding an electron into that 2p orbital is going to require energy to make it unstable. Another element is nitrogen, because its 1s orbital and its 2s orbitals are filled, and its 2p orbital is half filled, which actually makes it quite stable. So adding an electron here will set off the balance and will require energy instead of giving off energy. The last one is neon, which is a noble gas, so it's clearly stable, and its 1s orbital, its 2s orbital, and its 2p orbital are all filled. So that last electron would have to go into 3s orbital, which would make it unstable. So these are the 3 exceptions.